Great. Once again, good evening and welcome to this session. As you are aware of, the purpose of this session is to share new technologies to our college students, and there are few attendees from NXP who recently joined us, so beneficial for them to understand what's the latest things NXP is working on. And this is basically a brief introductions of new technology. If you want more details, if you want more deep dive, if you want to work on it, you need any support, you can write to us, or maybe you can go through our website www.nxp.com to understand, and you can order samples from there. You can go through the videos and all those things. Can someone start video of today's session? Is already started. Perfect. Okay, my brief introduction is, as Akhil mentioned, total 25 years of experience. And I am working in this automotive domain for almost 14 plus years. And right now I am handling automotive software team here, including boot ROM, security firmwares, and different other types of software to enable SoCs. Today's session is the communication engine. So I will first show you some video where you can understand why communication is very, very important in the car. Car is not just a car. And then we are going to discuss different use cases, challenges, and a brief introduction of the vehicle communication. And then we are going to deep dive on the high level view of the communication engine, then how the host interface is going to interact with that. And then we are going to discuss about the integration of the software. AutoSAR is very popular in the automotive segment. Then what all products are released onto this one. Then the enablement sample application. There is one demo to showcase the difference between a traditional way of communication in the automotive and now the smart communication engine. After then we are going to discuss, we discuss a lot of stuff. If someone want to work into this domain, or he or she want to shape their career in this domain, what is the things which you have to sharpen your skill sets and all. We will touch that those things into the brief. With that note, before jumping on to the real content, I want to excite you with a small video. Maybe I'm just sharing my video and audio also, although it is merged, 2 or 3 videos are merged together. So there may be some glitches in between, but the speed is also, a little bit high for the audio, but you can able to understand. I'm just starting this. If there is any issues with audio or video, please, let me know. Hope audio is audible.
Yes,
Is
sir.
perfect audio video?
Yes.
Perfect, great. So you can see the different types of applications on the car. Basically identifying the options. Now you see the power of NFC communication. It is all, a lot of data is sitting in the phone. You see the latest feature. You can order the pizza or maybe something else. Payment done. That's right. So this is the type of communication with different types of applications and all. Now our next video. This is mainly the new electrification and how autonomous car and all those things are integrated. ultimately the lot of data is going to be transferred, lot of data processing. The complete view from outside is visible. 360 will give you your car. Latest situation in your car. This is the new, basically speaking, the design. This is captured from the new Ford vehicle. This is the dashboard of this F-150 is the name of it. Very popular in here. Our latest devices provider that we have so giving you this real-time data, a lot of data processing is happening in the background from different zones, different area of the car. This is the complete dashboard inside. This is basically a view of how many types of sensors, how the data is going to be moving to the central processing, to the global processing, and then transfer the data outside the car. Taking decisions based on the sensor data. Moving sense, scan. So hope you enjoyed the video and trying to understand that why the smart communication is required inside the car. So we will touch few more, areas now in detail. This is just to give you the real, glimpse of the real-time operations happening in the car. So now just to give you the glimpse of, on the left-hand side, you have different types of applications: vehicle networking, infotainments, ADAS, advanced driver information assistance systems, different types of connectivities inside the car, outside the car. And here we just sharing the type of data speed we are looking for, because there are certain requirements where 1 Mbps data rate is okay. At some places in different applications you need 1 Gbps, 20 Gbps, 10 Mbps. So different types of applications need different types of throughput. So on the right hand side, we just want to show you the LIN, the initial in, maybe you can say that 10 to 20 years back, the LIN communication, which is 20 kbps. Then, we advanced that channel to CAN, which is, giving you the 1 Mbps type of data rate. Then FlexRay, which gives you 10 Mbps, then Ethernet, which is 100 Mbps. And nowadays, there are a lot of ports giving you the multi gigabits of, data transmission within the car itself. Here I am also taking few examples of, today, it's not today, basically, few years back when our radar is giving you a sense as a signal, then the signal is going to be interpreted and, just displaying on the cluster, and then driver is going to take the decisions. Sometime it missed and that, causes accidents. But going forward, everything is going to be, automated, and the central gateway is going to collect the data. Based on that, the artificial intelligence, machine learning, a lot of things are going to be implied into that, and then will be out of the loop. the car is going to take the actions based on the circumstances and all, based on the decision making, based on the training, based on the AIs and all. They are going to be improved based on the experience and all. So this type of infrastructure is already, in testing, either in the development. A lot of R&D is happening around that. Now, in this slide, I just want to show you there are two type of, you can say the architectures, which is very popular nowadays. Few sets of customers are looking for the domain-based architecture. When I'm saying domain-based architecture means like one domain is related to the powertrain. Powertrain means the engine system. Then you have the advanced, driver, the things which is related to the driver assistance. Then you have the connectivity, and then you have the different types of domain controllers for infotainment in vehicle, rear seat stuff. That is, one of the area. Then another area is for body and comfort. And then all of these are, going to be, you can say, communicate with the service oriented gateway. And this service oriented gateway is going to be connected with the cloud. And then the exchange of data is going to be happen. The other architecture is basically the car is divided into different zones, and each zone is going to be control, manage, tracking, monitoring the data happening in that area. And then our consolidated, data is going to be sent to the central domain. That central brain is going to analyze that data and then taking, connecting the data from outside, giving signal, taking controls and all those things. So these two types of main, architectures are very popular as on today. Few guys like BMW and all others are using, let's say, domain based. Then some other guys, for different applications using the zonal vehicle architectures, and NXP is supporting all these architectures. On this slide, we just want to show you, it is like X-ray scanning of the car, how, different types of cabling inside the car. And when we are, converting from the gas-based combustion engines to the hybrid, then hybrid to electrical vehicles, this is very important that we have to reduce the weight of the car by reducing the, wire harnesses there. Plus, we have the data is increased many times. I will, share you some data that how much data at every second we have to, transfer or exchange or getting the data, sharing the data. Different types of sensors are pumping a lot of data on the real time processing required, real time actions required. So on the bottom of this one, we are just sharing you sense, think, act in the different ECUs. Just a data for you. As on today, in the high-end cars, there will be more than 300 plus microcontrollers or microprocessors to do different types of, task within the car. In this slide, I want to just share you, there are, 38 million connected car in 2018. This is a very old data. This is going to be multiplied, several X nowadays. And vehicle data, 4+ terabytes of vehicle data is generated per hour. Can you imagine how much data will be there, how much processing, how much, storing, transferring to the external, internal, different other nodes within the car? Very complex system. Now, data is there. When data is there, a lot of opportunities to new applications. So predictive maintenance. Right now, your garage or your, maintenance guy is calling you, sir, your maintenance due. Now your car will tell you do regular maintenance or the predictive, proactive maintenance, or maybe sometimes they will, regular diagnostics are going to be running within the car and they will tell you the predictive maintenance. Advanced vehicle diagnostics. Your car, will diagnose most important part, and then it will suggest you that this is problem, or maybe you can, change the oil, clear the filters. Your car performance is not so good. You will do XYZ actions onto that. So several things are going to be suggested. Then usage based insurance. Insurance is also going to be smart because a lot of data is there. They know your profile, how you are driving the car, how serious you are, how good you are maintaining your car and all. And after then telematics and the fleet management, a lot of data, will be required on a real time basis. Then customers 360-degree assessments, then uses and feature analytics, public safety, and all those things. After then, because now car is connected, a lot of data, a lot of area where, a lot of sensors, then there will be a possibility that at the first level of release, the software is not very perfect. The firmware loaded is not 100% okay. You need over the air updates. You are driving the car, you don't know even the car is going to update, the data. Edge to cloud data, analytics, virtual ECUs, then different types of, intrusion detection preventions within the when data is, changing the nodes. You need all these monitoring at different locations, data logging with, time stamping when that happened, when that, malfunctioning is happened, different types of forensic checks and all. Centralized vehicle security and safety is a very, very important features, the OTA, because you are updating the firmwares and all, over the air. You need a very secure channel to update your car firmware, and a lot of new features are going to be introduced, slowly. This is a view of how many sensors. This is just, you can say that it's not completely, it is a main, you can say that the main sensors mentioned here, starting from the steering, car alarm, airbags, and the comfort of the seat, different types of controls to handle the seat, suspensions, tire pressure monitoring systems, different types of radars, put it on around the car, vehicle movement tracking, sunroof controls, navigations, heads-up display, rolls over detections, airbag, night vision. I'm not going into each and every sensor. You can understand the type of sensing within the car. Then the connectivity, power will be provided, lot of, protection there, lot of safety, security, data transfer, data instrumentation, and then taking actions, connectivity. Car is just like uh, more than a computer, compute engine, you can say that. Now, it's not just the internal processing. We want a very, comfortable, very high-end system within the car, not just audio, video, everything, real-time processing, real-time signals, real-time assessment. So you can see the picture here. This is the real picture from, the car which is under testing and all. So cockpit, the car cockpit is, you can compare with the, aero, cockpits, the multimedia, very high-end multimedia is there. Then media sources, different types of media sources from the open source. You can directly download from the clouds and run, and all those types of features will be there. The real satellite radios, very high digital radios, or different types of audios, and all these interfaces are, available there. And this all is, different types of hardware is also there to control, manage, monitor, data transfer, and then different types of services, gesture controls, voice control, the different types of radio and audio control, machine learnings, driver awarenesses, safety, camera, vision, audio. So a lot of, you can see what the car is, what different types of engine you are basically driving with full, comfort, with peace of mind and all those things. Now, this all, I just give you the background of why we need a smart communication engine within the car. This whole background, the video shows the different types of applications which need how much of data. Then we explained to you that this data will be associated with different types of applications, how much data we are transferring from the cloud, what are different types of applications and all. Now we are jumping on to the real topic, the vehicle communications. So we already discussed here. You see the bottom pictures. Long time back, I can say use the word long time back. The node-based communication, maybe like example, signal to the wiper, signal to the window. So these all type of master or slave type of configuration there. Now, not now, basically you can say few years back, then we thought of let's have some small gateway, and then gateway is interact to the different types of groups and all. And nowadays, basically, we have different, small gateways. They are taking their own decisions, taking controls, doing the different functions, and some data is going to be transferred to the centralized guy who is going to, support the different types of applications within the car. And going forward, the last block is basically the zonal management, and then data is going to be real time processed and then sending to the service oriented gateways there. So this is basically the trend. And it's not just, data. You have to secure the data. When data is changing nodes, it should be completely secure data. Otherwise, a lot of issues. So message authentications, a data source validation. Then after authentication, you have to give the controls. You have to share the data. Then a continuous, intrusion detections and preventions, and do the time stamping of that one. So these all are the features of the smart communication engine. And different types of connectivities, because one connectivity can't work for all types of different applications. So CAN, LIN, SPI, FlexRay, Ethernet, everything is supported. So this is just a background, and there will be a lot of IP, lot of infrastructure in that. Then different types of channels there. This is the top level of view. Now, here in this slide, we just want to show you a communication engine, which is having a very low latency, because time is very important to take, analysis, instrumentation of the data, then transfer to the location, and then take the decision, and then take the connectivity, and then, do the before that security and safety is also involved into that one. So this communication engine is a subsystem which is composed of both a hardware and the firmware. And on top of that, there will be different types of softwares which is running along with that. And the different types of LLC, the low latency communication engines, which include support of different types of infrastructures like 16 CAN interfaces, 4 LIN interfaces, FlexRay interface, 4 SPI interfaces. Then there will be a smart implementation where you can, reroute the packets without much processing. Then there are a lot of hardware accelerators inside that to speed up the things. And then there will be different types of, as I suggested you, different types of routers, CAN to CAN, CAN to Ethernet, Ethernet to CAN, and then security offloading, different types of safety features implemented onto that. So these all are the future features from, from the top level, if you can see what is the architecture of this block. Then, yes. So on this slide, we just want to give you a comparison of the previous. Let's say in the previous you have the CAN IP, SPI, then Ethernet and all those things. But a lot of CPU core time is involved into that one. Now, but with this, advanced communication engine implementation, the offloading is done. The core is going to just initiate, means fire and forget. You just initiate the things, and then the engine is going to take care of all the activities, which is, configured through the firmware using the hardware accelerators. And this communication engine provides, firmware which is defined the host, interface, and which can be changed based on the requirement of the applications and all. Different types of flex can interfaces there. The firmware is inbuilt loaded into that one to do advanced filtering, consistency checks, mirroring, routing, a smart communication with the host, proper uses of the hardware accelerators to speed up the things, to doing the time stampings. All this type of functionality is offloaded into this. Now in this slide, we just want to show you on the left hand side, this is the traditional way of how the different layers are going to work. The hardware where you have two CAN channels. If you want to reroute the a packet from one channel to other channel, the CAN driver, then the CAN interface, different types of routers. You have to extract the data, then again uh, convert that into a different protocol and all those things, and then rerouting it to the host. But on the right hand side, if you compare with this communication engine, if you want to reroute the data, no need to go to all the layers. It is just if you see the red dotted lines here, basically it will rerouting the things just from one CAN to other CAN channel, or maybe one type of interface to the different types of interface. What all interfaces is defined there to this one. So this is a very important feature where the main core, the main application core is not busy. It is just, configure the things. The transmission and receiving is happening. Internal smart communication engine is handling all those things. And then it can be observed that easily the, sort path of the LLC internal routing from the on the right hand side, which we are showing it here. So you can, here we given you the reference of how the software, it's not just hardware. Basically, it's a combination of hardware, software, and all those things. And everywhere the processing improved, the data accuracy improved, security increased, safety increased, and the time is less. So very beneficial with respect to the overall automotive applications. So this is just a top level view of that. Now we are going to jump on the architecture and the high level view of what this communication engine is. Okay. So on this page, we are just showing you. We already discussed that different types of interfaces in this engine. This is the top level block diagram, or the you can say architecture block diagram, hardware block diagram of the smart communication engine. So here you have different types of blocks like CAN interfaces, LAN interfaces, SPI interface, flex array, and then there is a hardware module called time stamping for 1588 time bus. So here you have a different cores, core 0, core 1, core 2, core 3, core. These all cores are associated with the different types of interfaces. And these cores are basically the ARM Cortex M0 Plus cores. And different types of shared memory is associated with every core, starting from 8 KB to 64 KB, and you can configure, you can program. Firmware is also given by NXP. You can use those firmwares here, and then the complete drivers and all those complete infrastructure is available. Apart from this, you can see the different types of CAN channels, different types of 16 CAN channels, because the CAN is most popular communication interface channel within the car. But going forward, it is going to be flex array, Ethernet, very high end, very high data transfer is going to be required. For one flex array, 4 CAN, LAN, 4 SPI. These all interfaces are available in this one. Then you have RX frame receptions, then the transmission frame receptions areas, different hardware accelerators to handle that. And this connectivity with this is the central bus is connected with the central bus of the processor, and then you have connectivity with the Ethernet block, which is PFE in one of the SoC. Then you have the security block where it is going to be interact for the secure packets. The encrypted packets are coming. You have to check the packets, decrypt it, and then transfer it to the destination nodes and all. So this all connectivity is there. Then there is 100 plus people channels there to handle the data flow there. Then extended memory area, up to 300 plus KB is available for intercore communication purposes to interact with the host. And this entire LLC communication, the smart communication engine of low latency, is interfaced through the XRDC domain. This means that it is not possible to do any isolations inside the LLC between the components like CPUs, peripherals, or different types of memories and all. And different, you can debug all the codes if some issues there and all. And development, very different types of development platforms are available. We have our own design studios. We will discuss this in our different slides. So this is our top level view of a very high level view of the communication engine. Now here, as I updated you that we have uh, different types of interfaces available there, the CAN controller, LIN controller, FlexRay, SPI. So these all blocks are, connected to our different core. A shared memory is associated with that one, and different types of host are drivers there. And the smart communication engine, we are writing the communication engine firmware, which is architectures to handle all the four independent containers which are mapped with the different serviced buses. And then the core, which is ARM Cortex M0 plus core, it is handling the different types of transfer protocols there, and the entire architecture of this communication engine controlled by the firmware, which is then associated with the AutoSAR and different MCAL drivers and all. And then the entire architecture of this communication firmware was based on the idea to have no data copy operations, between when interacting with host and this communication, engine. And in order to assure that the condition, it was decided that the data is to be placed on a shared memory, is accessible, and to transfer only to the pointers to the indexes where it is between the LLC and the host. And the development focus was on the CAN, firmware, and it is currently the most requested module, or maybe you can say the heavily loaded a block of this functionality. And each communication protocol has a different types of number of hardware element which are used to implement and needed to interface with the host. And this is mainly in the case of CAN. And in the case of FlexRay or the SPI controllers, which is included in the communication engine, they are SSS and controlled directly from the host side. And the role of this communication engine is controlled by the firmware, which is loaded in these blocks, and it is just to forward the needed interrupts because the interrupts are not routed to the host. So this is a brief operation for the high level view that how things are going to be managed there. In this here we are just describing you the LIN flags. LIN flags is loaded with a firmware inside this controller for doing the transmissions and receivings, and it used the shared memory for core to core module and intercommunications. and to share with the host interface. And this core-to-core module is needed basically to generate the interrupts from one core to the another core. Then the LIN firmware basically implements the basic features which is required by the communication engines in the form of transmission, receiving, interrupt based transmission, or the polling based transmission, that depend upon how the applications are going to be configuring this hardware. And it is able to behave like a master or a slave on the LAN bus. So this is basically some notification, and based on the notification the host will send the commands and control this complete transmission, and data is exchanging from one node to the other node. Here on this, it is basically the FlexRay controller, which is also part of this smart communication engine, and which is accessed directly from the host side using with the AutoSAR FlexRay driver. And this FlexRay driver basically controlled with a firmware which is loaded onto the FlexRay controllers. And this firmware is forwarding the FlexRay controller interrupts to the host driver via core-to-core module communications. And this is required in order to work around specific hardware restrictions, which means that the FlexRay interrupt is not accessible directly from the host side, and forward interrupt is used by the AutoSAR FlexRay driver to send and receive data synchronized with the FlexRay communication cycle from the bus. And one more important thing is, maybe in next slide we'll discuss that the communication engine plus the standard CAN and FlexRay modules are parallelly. You can work, and they are not going to create any issues or noise related problems or anything within the power transmission. Here, this is an example of how SPI controller. So as we discussed in the previous also modules, the SPI is also having their own controllers, and the situation is very similar like the FlexRay case. Firmware is going to be loaded into that one, and then forwarded the interrupt, which can be used by the AutoSAR SPI driver created by customer to send and receive data synchronized with the SPI communication protocol. And currently no hoster driver is available for this one. So this is for the SPI interrupt-based communications. So this is how the high level firmware is architected, and how it is the notification is going to the host. Now, how the host is going to react based on that. So we are taking the example of the CAN. So in this basically there are different stages like configuration, then transmission, reception, and then the data. Different types of accessing the data through the polling method, through the interrupt method. So I'm going to discuss all those things step by step. So here we are configuring first. So write the command ID and the command parameter into the shared memory. Once you did that, then write the channel ID. After writing the channel ID, you have to check continuously either in the polling way or in the interrupt way, that whether the flag is raised or not. If it is raised, then clear the FIFO is cleared by the firmware in order to detect the completion of the command processing by the LLC firmware, and then read the command completion status from the shared memory location. This is how the smart communication engine is doing the operations, and then the smart engine interacting with the host driver or the application shall follow the configuration flow. This is basically just showing you how the things are happening. Then how the transmission is happening. Once we configured the hardware, the core is associated, the polling or the interrupt flag is associated with that. The FIFO buffers and all the things are associated. Then you have to read an index to an empty transmit descriptor. This is the first step after the configuration, how the transmission is going to be happen. Then you have to write the fields of the transmission descriptor and extract the index to the message buffer table. After then, the third step is basically write the can frame content into the referred entry from the message buffer table. Once that is done, then you have to basically write the index of the transmission descriptor into the channel. And then after this step, you will read an index into the acknowledge information table, from the channel track FIFO that this operation can be done in which state, either in the polling or the interrupt mode. Once that is done, then read the content of the referred entry from the acknowledgement information table and then process it. This is the basic steps how the transmission is going to be happening. Now, once the transmission is done, you can, or maybe parallelly how reception is going to be happen. So first step is, read an index to a full receipt descriptors. And once, the information is available there, after then you have to read the reception descriptor content and extract from it the index, into the can message buffer table. Once that is done, then read the content, of the full reception method buffer and then process it. After the processing, write the index of the receive descriptor to the RX FIFO, RX in FIFO, in order to send it back to the LLC to be reused for the other operations. So this is how you are going to do first configure it, and then how the transmission and receiving is going to be happen. And there are, as you are aware of, we discussed there are two ways. One is the interrupt mode stuff and the polling method. How the interrupt mode is happening in the notification flow. So here an interrupt is generated to notify the FIFO that when a new entry is available. And once this is available, the host reads the new entry and then an index to the noticeable tables. And you can use the previous read index in order to access the notification parameter from corresponding tables and process the other notifications which are ready to serve. And then different types of notifications flags are there, which you can during the assessment you can see what all notifications will be there. Based on that, you can take the actions. So this is a type of interrupt method. And now in the polling, basically in a very similar way, basically you can poll it, and once the host checks the flag is there, it is set. The host read the new entry which contains the index of the notifications, and then once that is done, then you can use the previous read index in order to access the notification parameters and from the corresponding table and process it. And these are the different examples of different types of notifications, like the LLC error, FIFO, it is empty, full, not available, which type of protocol. Then you have the hardware commands, so many status flag is there. You can read it and take the control and understand the behavior of the system. This is a typical flow of how the things are happening in the smart engine. So the application core is just initiating the things, and rest everything is managed by the cores which is inside the communication engine. And these cores are going to be managed by a firmware which is loaded onto that one. And there is a OS which is running at the applications level. So now we are going to discuss about how to integrate this with an AutoSAR. So NXP basic, AutoSAR is AutoSAR is basically, you can say that it is a automotive OS which is very popular in automotive applications, very reliable. You can say that, and most of the automotive customers are using this. So NXP is also releasing the base layer. So here you can see that there are certain blocks which is green in color, and there are certain blocks which is in blue color. So mostly green color blocks are the NXP is supplying this complete infrastructure, because it is you can say that the AMCAL drivers, which is basically directly interacting with the hardware. And then on top of that, there will be different types of service runtime environment components, which is mainly giving providing different types of services. And then this complete infrastructure is going to be on top of that, different applications are going to be routed. You're going to use this one. So the green color marked are the NXP deliverable, and we are saying that it's a real-time drivers. And the blue color marked is basically the delivered with not with by NXP but by the NXP partner. So we are there are different partners who are developing the complete infrastructure, and they are using our MCAL components and creating a complete software infrastructures for them. Uh, we are working with different partners like Electrobit, Vector, Kpit. Nowadays, a lot of other guys, and in some cases the big customers are also developing their own products, or maybe complex drivers. By using our driver, they can create their own infrastructures. So in order that customers to use this smart communication engine, it is needed that a perfect combination of firmware and software is going to be integrated and work together. And performance is very important. Time is very important in the automotive applications. So considering all those things, uh, NXP is providing the firmwares. NXP is providing the real-time drivers, so that the best utilization of hardware resources, because a lot of hardware accelerators there, a lot of smartness we implemented into this one. So combination of hardware accelerators, smart communication engines, firmware, then the you can say real-time drivers, and on top of that the different types of services, and on top of services are different types of applications. This is the complete end-to-end, you can say, the block diagram of a typical automotive application software. Now on this slide, as we talked about, the AutoSAR MCAL drivers are delivered, in the form of the real-time drivers product as a separate release, which includes the drivers for all these blocks. So, in the microcontroller, you have the watchdog, the core, general purpose timers. Then you have different types of memories, flashes, or electrically erasable E-square proms and all. Then you have the different types of ports where ADC, PWM, I2C, so different drivers for that. This all what I'm describing you is a part of the real-time drivers. Then you have some complex drivers like the PMIC, which is a supervisory circuit to manage the complete power modules there. Then you have different types of communication channels. Then the very important part is the crypto driver. You have the crypto driver there. On below that, they are going to interact with the security engines and different other types of safety frameworks are there. And then traditional, you can say the communication blocks where the communication drivers for CAN, LIN, SPI, Ethernet and all. And then on the right hand side within the green block, this is the smart communication engine where all this traditional, you can say that not traditional, the different types of communication interfaces is part of the part of the communication, smart communication engines. All are integrated all together. Main core is just initiate the communication, and then everything is controlled and managed by this smart guy. So this is the overall, you can say that what all is part of the real-time drivers and the communication engines and all, and how this communication engines is going to be controlled, managed, monitored, tracked, and all smart implementation there. Here, we are saying that we discussed what is the overall real-time driver. Now, how the different firmwares, the different real-time drivers is going to be integrated on top of that. So for platforms, including both means FlexCane and the smart engines, the AutoSAR standard allows that the multiple MCAL drivers for different CAN controllers will coexist. And this means that you have to configure and compile both into single applications running on, on the same chip. So the different CAN block and the CAN block within the smart engine, basically. So both can run parallel. This type of feature is implemented into the AutoSAR stack. So this means you can configure, compile both into a single applications running on the same chip, and mixing calls from two different CAN drivers is managed by the CAN interface module. And this only request for MCAL driver is to use each exported element like APIs, global variables, different configurators, different types of configurations and all. And in order to allow the separation between them during compiling time and the runtime, this is how it is managed, with the hardware and AutoSAR infrastructure. Okay. So till now we discussed the NXP provided software firmware infrastructure, and then how it is going to be integrated in overall AutoSAR framework. And here basically one top level architecture of how one of our partner, which is Electrobit in this case, so how they are going to basically enabling all this infrastructure. So this is basically the top level block diagram of describing the configurations flow using Electrobit Trasos. So Trasos is a configurator tool where you have to configure the hardware. And after configuration, basically this will generate the header files and C files and all. And those all are going to be integrated with the NXP provided smart communication CAN drivers. And once everything is integrated, then the user code from the application layer will take control of that, and then using that into that. And the user input is captured by using the EB tool, which is the Electrobit Trasos tool, based on the .xtm files. Then this tool generate .h.tc files, configuration files. Those are then compiled with along with the smart engine CAN drivers, and then generate code in order to generate the final binary image of the host application, which is interact with the communication engine firmware, which is on the bottom of this. This is the firmware which is loaded on the smart engine for different interfaces. Okay. Okay. On this page, basically, it's not just our partners are providing the complete thing, but we have our internal ID, which is S32 Design Studio. We have a configurator tool inside the Design Studio also, and by using this Design Studio, it will again, in a very similar fashion what the Electrobit Trusses tool is generating. This tool will also generate a .c and configuration and the header files for that, and then this complete files are going to be build along with the cane like in the previous case, and then it is going to interact with the LLC firmware. So we have a Design Studio based configurator tools and generate the binaries to use the smart communication engine. So this is all about the firmware, software, hardware, AutoSAR, how it is going to be interact, what all types of partners enablement tools, and the internal NXP Design Studio tools can be used. Now I'm just giving you, not going into the details, but how we are releasing it. As I updated you, you can get all this information on our nxp.com, and from there you can get the information related to the NXP related the MCAL drivers, RTDs, the DS Design Studio based configured tools, and all the different types of videos and complete infrastructure available there. One very important information here is a communication engine Fdk is available. So by using this firmware development kit, you can configure the communication engine, and you can develop a complete applications which is useful as per your applications. So this type of complete enablement infrastructure is available from our side, and you will get more information from our website. So this is just a glimpse of when you are going to, our nxp.com, you will search the things, and this product information will be available from the automotive software, LLC software, different types of hardware, and how you can enable what all applications, different types of firmware, how to, manage 4 cores, different types of applications, nodes, and everything will be in a packaged form. You can get it from there. So mainly you can say that there are two different release packages. One is LLC, which is Smart Communication Engine Enablement, and then the Smart Communication, FDK, which is Firmware Development Kit. And both you can download it from NXP website. On this page, basically, as we discussed, the Firmware Development Kit is basically composed from all boxes from the blue and red areas, so that you have the clear visibility that what all is part of that. So FDK is intended to be used by customer which wants to extend the existing features and add their own features on top of that. So this is, a tool. And then in order to add new features, the customer shall, create new source files, which calls the APIs, which is exposed by the smart, communication engine IP drivers. And this is already exercised by some existing components from the top area of the block diagram and as mentioned there. So both the combinations is available for customers. They can use our firmware, and they can write their own drivers, and our partners can also do the same thing there. So the IP drivers, all the smart engine drivers will be provided by us, the firmware, so that it can be control the accelerators, the hardwares, and all. This is the deliverables from our side. And if you go through our website, you will see certain examples here, like, how you can transfer the data, routing the data from one CAN to the CAN number 0, and then transfer data to the 15 to 14, or maybe from 0 to 15, and then different types of routing by using these smart engines, and then the uh, CAN to CAN routing sample applications, which is available as part of the enablement release. And this configurations routing rules are configured in CAN smart engine configurations drivers and firmwares. And the sample application, basically the host core sends a frame to one of the CAN channel, which is received on another CAN channel, and they are wired through a loopback, which is mentioned on this picture. And the frame received on CAN 0 is going to be configured for internal rerouting to the CAN 15, and then or you can define your own routing configurations to understand how this is working. Then the complete details will be there, although I'm not giving you the complete description of this one, but the complete details, the videos, the complete descriptions, all is available on our websites. This is about the packages if you are interested in this development. And then this here on this page, we just want to show you that just a minute. So this demo is basically to show you with the traditional way of handling the packets, and how the packets are going to be handled in the smart engine. So on the top side, you have the previous generation devices where we are transferring the data, and the data is going to be processed, and then receiver is showing how the picture is going to be received. And you see on the bottom there is a smart high-end device where the smart communication engine is inside, and that communication engine is processing the data, and this data is delivered on the destination. You see, you can compare, although it is not a very real-time presentation, but you can see the delay between the previous and the latest technologies. And on top, basically, we are showing you in the previous generation controllers or the microprocessors. This basically you can see how the core is loaded. And you see the other picture where the smart communication engine is there. The application core is sitting idle. It just initiated, and then the engine is managing the complete stuff. So this demo basically compares the capability of the previous generation devices versus a new generation devices having the smart communication insights. And this demo is related to can-to-can routing packets. And this demo used two generations microcontrollers, and uh, each device is processing the same data packet, same interface, same can interface at the same speed, only the processing which makes a difference. So this is basically a brief description of this demo, that by using our K series controller, we are generating a packet and then we are transferring to them. If you want more deep dive on the latest technologies, how we are basically uh, enabling the different types of technologies in the vehicle, you can go through our website, which is nxp.com/vehicle architecture academy. So you can see a lot of content with respect to the new vehicle, what NXP is doing in the automotive, how automotive industry is transforming, and how we are supporting them. So this is basically related to that, and a lot of content, a lot of videos you can see there. Now, this is all about today's presentation of what we just describes this and all. Now, a very important thing is, as I saw most of college students are also part of this presentation. They are attending this. So if you guys want to shape your career in this domain, so there are different areas which we can see this like the SoC design. So SoC design is basically you have to design a system where the IP design and then different types of other domain into that, like DFT, front end, back end, STA, so many different you can say a skill set which is required to build SoC, and then pre-silicon, post-silicon verification, a lot of areas where you can shape your career, and NXP is one of the top 10 semiconductor companies in the world. And we are operating from 4 locations in India: Noida, Bangalore, Hyderabad, Pune, and state of the art infrastructure is there, state of the art very high end labs there. So it's not just we are designing, we are also validating, verifying, and very high end software engineers who are developing, validating, packaging, releasing the complete end-to-end infrastructures. Nowadays, customer cannot just use your microcontroller, microprocessor. They are so complex that the hardware accelerators, the firmware, the real-time drivers, and the complete infrastructure required from them to time to market, and reduce their development times and all. So for that purpose, if you want, one way is you can shape your career in the SoC design area. The other is you can shape your career in the software firmware development. So C, C++, Python, real-time operating systems, AutoSAR, Linux, Android, QNX. These are the languages you can learn. Then different types of cloud infrastructure nowadays required, as we discussed, a lot of stuff related to the different types of applications and data transfer, data sharing on over the air updates and all. Hypervisor, virtual machines, data structure, cyber security, safety. A lot of stuff is areas where you can shape your careers. First you understand in brief what all these things are. Latest technologies like artificial intelligence, machine learning, big data, neural networks, voice recognition, gesture control, augmented reality, and then a lot of other areas where simulations, emulations, field testing, quality assessments, user experience designs, enabling customer support. A lot of other domains are there. So this is a view of the complete embedded system profile, starting from the SoC design, then different types of firmware, softwares, safety, security, and then enabling customers, field engineering, and all. This is a top level view of if you are interested in this domain. These are the areas you can pick, one or two, identify certain things, and then shape your career. NXP is, welcoming all of you, and the purpose of sharing this is, one is excite you guys that what we are doing, and then we are suggesting you that how you can work along with us, and if you need any help, any support, any infrastructure, because a lot of startups are growing from the colleges itself. People are working in a group, they are enabling, and we are also as NXP, Sanjay is a very dynamic leader who is leading. He's a country manager for NXP India, and he is always ready to support. You can follow him for latest updates and what all NXP is doing. We we are regularly visiting different engineering colleges, and like me, most of yours, the NXP is a dream company for you. So NXP senior leadership team is ready to welcome you. And with this note, I am stopping here, and we'll take questions now if you have. Thank you for your time and patience.